Good morning, or afternoon or evening, whenever you're watching this. It's morning for me, and today I'm recording from my office, and I'm not super stoked about the lighting in here, but I'll make the math larger and me smaller in a moment. Just wanted to welcome you to Chapter 3, Section 2 in Elementary Calculus, and we're going to be talking about continuity here, and I'm going to use some slides where the material was adapted from a calculus book called Calculus with Applications by Greenwell, published by Pearson. And the topic today of continuity is not a super difficult concept, but it's very important in the study of calculus. So let's go through and look at a couple definitions and a couple examples, and then we'll knock out an applied example at the end and make sure that we see how this particular topic fits into maybe some real-world applications. I'm just trying to get my levels right before I carry on. There we go. So we're still talking about functions, and a continuous function is, in a very sort of easy to understand way, a continuous function is a function that you can draw without lifting the tip of your pencil. Most of us are familiar with holes and asymptotes in graphs, and those are examples of discontinuity, a hole or an asymptote. And this definition of continuity contains some notation that we've been seeing recently about limits. And we can say that a function is continuous at a particular x value where x equals c, as long as the following three conditions are satisfied. Our function has to be defined at that point, and the limit must exist at that point. And remember that if a limit exists, that means that the limit from the left is equal to the limit coming from the right. So the y values are both trending toward the same y value as our x values come in at, in this case, a c value from the left and from the right. And I talked about that in the previous video, 3.1, about limits. And the function, number 3 here, says the limit of f of x as x approaches c. Those y values have to be trending toward a y value that's equal to if we just took the c value and plugged it into our function. And we'll see an example of that. When a function can be made continuous at a specific point simply by defining or redefining it at that point, the function is said to have a removable discontinuity. Let's make sure that we've got a clear understanding of the removable discontinuity. So if you can take a function and modify it, following the rules of mathematics, of course, so that you maybe don't encounter division by 0, for example, it is possible to, potentially possible to evaluate the limit by direct substitution. A function is said to be continuous on an open interval if it is continuous at every x value on the interval. That makes sense, utilizing the definition of continuity that we just looked at. And then when we start talking about a closed interval, where we have little closed circles at the either end of our curve, or square brackets that make sure to include the x values at the end points of our curve, it's a little more labor intensive to declare or determine if that function is continuous. And these two bullets tell us how to do that, and then I've just drawn a very rudimentary sketch of that situation. So here we have a closed interval because we have these, hold still, because we have these sort of shaded dots at either end. If these had been open circles, then that interval would be open at A, open at B, but I've closed them by shading in those circles, so we're including A and B in the interval, and you can see the square brackets that are happening there. And so in order to be able to say that a function is a function on a closed interval is continuous, then in addition to the function needing to be continuous at all of the x values between a and b, we also need to satisfy these two conditions. At this first endpoint, as our limit approaches from the right, so if we're on this curve and we're coming in from the right, our y values must be trending toward the same y value that we're seeing when x equals a. Could we be working on a closed interval where this point, if my eraser will work, where this point is not here and it's actually defined up here and we have a little opening here? If this were the scenario, then the limit as x approaches a from the right for whatever function it is that we're working with, f of x maybe, does not equal f of a. So again, we're on this curve starting maybe from here, and we're moving to the left, approaching that open circle, and our y values are trending toward maybe a y value of 2. So this side of this equation would be equal to 2. However, when we finally arrive at this x value of a, you can see that the y value at a is actually equal to 3. And the problem there is that that would not satisfy this statement as we try to prove or demonstrate that our function is continuous on the closed interval. Another way that we could say that is, if I can get rid of some of these red lines, not lifting my pencil, not lifting my pencil, not lifting my pencil, not lifting my pencil, and right when I get to that first endpoint, the x value of a, I have to lift my pencil and come up to here. So it was continuous everywhere except we blew it right there at the end, or at the beginning when x equals a. So we do need to have this colored in so that our function is continuous even right there at the endpoint. Alright, so that is continuity on a closed interval, and we could have that same conversation about the x value of b. As our, can't write with an eraser, as our x values are approaching the right-hand end of our interval, and you would approach the right-hand end of the interval from the left, the limit has to be approaching the actual y value that's present there right at the end point, when x equals b in this case. These are some really nice rudimentary examples. Here we're being asked to find all the points where the function is discontinuous, and you see that we have this kind of jump discontinuity here. We would have to lift our pencil and then move it up and put it down again in order to keep drawing that function. So it is discontinuous when x equals 1. There's a different thing that's happening here. The function is continuous, but it's not smooth, and we haven't talked about smoothness yet, but just so you've heard the term, the function's not smooth there. But that's not a discontinuity. This function has a couple of x values at which it is not smooth, but you could draw this entire function without lifting your pencil, so it's continuous everywhere. And this function has the other type of discontinuity that we're familiar with. This one has an asymptote, which looks like it's the y-axis, and we could therefore say that this function is not continuous when x equals 0. You would follow this curve in the upward direction, and then you'd have to lift your pencil and come back down here in order to hop on the curve and continue carrying on. So again, discontinuous at x equals 0 or when x equals 0. And then this is nice. We have some better diagrams, certainly better than the ones that I can draw. A really nice table of some different types of functions and their types of discontinuity. So the first one is a polynomial function, and polynomial functions like parabolas or a function that leads with x to the third, where we have integer exponents, positive integer exponents, those curves are all going to be continuous for all x values. Now, a type of function that we're quite familiar with is the rational function, and here the numerator and denominator are polynomials, but when you put one polynomial over the other in a fractional form, it becomes a rational function, and this type of a function is going to be continuous everywhere except where the denominator equals 0. So we would need to exclude those x values in terms of talking about where the function is continuous. In a rational function, if you could factor the numerator and the denominator and cancel out one of the factors from the denominator, the act of canceling it out would make that a removable discontinuity. And graphically, that shows up as a whole. A factor that remains in the denominator is going to manifest graphically as a vertical asymptote, and you can't dodge that one. But if you're able to remove or cancel out a discontinuity in a rational function, it only creates a little hole in the graph, and you would still be able to evaluate the limit there, because the function would look quite continuous except for that one point. But here, to the right, you can see that when you've got an asymptote, vertical asymptotes are not so subtle. And so we would have discontinuity there, and the limit would be undefined. This is a square root function. We've got continuity everywhere that the function is defined. So starting from an x coordinate of a, and then in this case going all the way forward to positive infinity. But if the curve were, of course, arcing out this way, then you would be continuous from negative infinity all the way up to an x value of b. And could you say that it is continuous even at its end point? If we did a further examination of the root functions, you would be able to say that. As a matter of fact, sometimes I put my hand down on the screen and it just starts moving things everywhere. This is a good indicator that it's continuous even at the end point, because we have the or equal to symbol there. So that would be a square bracket including the x coordinate at that end point. Exponential functions, where you have a number being raised to a variable power, those are continuous for all x values. And a logarithmic function, this is the sort of a parent function, so it's living in the first and fourth quadrant. A logarithmic function is continuous for all x values strictly greater than 0, this particular parent function, because in this case the y-axis is acting like a vertical asymptote, so our function's not even defined where x equals 0 here. So we definitely can't have continuity there if the function isn't even defined there. So a nice summary of different types of functions and some notes about their continuity. If you have a continuous function, or if you can make your function continuous, then how do you make a function continuous? Potentially by removing a removable discontinuity, like I mentioned, being able to cancel out a factor in the denominator. So if you have a continuous function, or you can make the function continuous, then you can evaluate the limit by direct substitution. Just take so over here you can see that we've got the limit as x approaches c, and if it's a continuous function, then that limit is equal to f of c. Just plug that c value directly into your function. When a function is given by a graph, your discontinuities should be clearly visible. The graphs that you see in a textbook or on an exam, if there's a hole in the graph, there should be some kind of pretty obvious little open circle that indicates the hole. If you graph on your graphing calculator, at least the TI-84 that I have, a hole is not going to be clearly indicated on that graph. It'll look quite continuous. I don't even know if you can zoom in far enough to where the calculator would show you a gap in your graph, but it's not going to put a little open circle where your hole is. So just be careful there. And a function's going to be continuous if the function's given to us in the shape of a formula. It's usually continuous at all the x values except those where the function is undefined. Or, and this is the interesting part, where possibly there's a change in the defining formula for the function. And we're going to see an example of that in the form of a piecewise function. We'll see one that works, and I think we get to see one that doesn't. So in example number 2, right, let's get to some actual applications of these topics I've just been talking about. Let's find all of the x values where this function is discontinuous. And since we're working with a rational function where the numerator and denominator are both polynomials, and very nice, this denominator has already been factored for us, it's going to be very easy to figure out the points of discontinuity. As you're pretty used to, we need to make our pen work. Why is my pen not working? Quick pause. All right, we are back, and I'm totally charged up. Let's do it. Find all the values where the function is continuous. Right, so I was saying that the denominator has already been factored. All we have to do is, since we can't cancel out any of these factors with any factors in the numerator, I'm going to set each one of these factors equal to 0, and those resulting x values will be our points of discontinuity. And you know how to do this, so I'm just going to do it pretty quickly. So when x equals 2/7, we're going to have a discontinuity. And when x equals 1/2, we'll have a discontinuity. And since these are discontinuities or factors in the denominator that we cannot cancel out, these are not removable discontinuities, and therefore on a graph they would show up as vertical asymptotes. The next problem is the piecewise function that I mentioned, and so we need to check and make sure that where the first, second, and third pieces join, so to speak, or I should say where the first joins the second and the second joins the third, we want to make sure that they would sort of match up. We don't want them coming in and not connecting. Our hope is that they'll come up and connect at a common point. An advantage to, oh, by the way, if you've read this thing and you're like not quite sure how to read this, that's the function. So it says find all values of x equals a where this piecewise function is discontinuous. It looks like these things kind of run together, but they don't. Okay, so the good part about this problem is, I'm looking at my levels again and it's peaking, so I don't know if that's sounding strange. I'll turn it down a little. The good part about this piecewise function is that the three functions, or parts of our function over here, each one of them is independently continuous. We've got two constant values and a polynomial, so they're all continuous. We just have to make sure that they link up. So you could try graphing these, and I'm sure that you could. Our function g is equal to 0 if x is less than 0, so that would be a line that's right on the x-axis. Y equals 0, it comes up to the point where x equals 0, but at least the first piece of our piecewise function is not defined at 0. The next piece is x squared minus 2x, and it is defined where x equals 0, everywhere from 0 to 2 inclusive, and I wonder what the y coordinate is if we were to plug in 0 into our function. And if we plug in a 0 into our function over here, then we would need to use this piece right here, because the right-hand side of what I just circled, this part, tells us, tells us to use the x squared minus 2x because we're plugging in an x value of 0. And plug in an x value of 0 over to here, you get 0 squared minus 2 times 0, that's equal to 0. So we would need to plot the point 0, 0 as part of the graphing of this middle piece of our piecewise function. And thankfully, let's grab another color here. Never enough colors. That would fill in this open circle right here, right at the origin. So now I'm drawing an orange, and it would be a parabola, and I don't know exactly what the rest of that parabola looks like. That's okay, but I can tell you that as this upward facing or concave up parabola continues moving to the right, eventually we're going to get to a point that has an x value of 2, and let's figure out what the corresponding y value would be at that point, since, again, this function does include or is defined where x equals 2. So take your x value of 2 and plug it into x squared minus 2x, 2 squared minus 2 times 2, and again it happens to equal 0. So if we go over to our graph here and we move out 2 points, we would be able to plot a point at 2, 0. My next question is, as we look at the third part of our piecewise function, is it going to link up with that second orange point that we just drew? So we're assuming that our parabola is continuous through here, and it is because it's a polynomial. But what about this next part here? If we take an x value that's larger than 2, let's say 3, and we plug it into this function g of x, so g of 3, I shouldn't be using orange. I need a different color again. Let's use green. G of 3 is equal to, well, for any x value that's greater than 2, this function is going to return a y value of 2. So g of 3 is equal to 2. What about g of 2.5? That's also going to equal 2. What about g of 2.00001? My point is that as our x values come from the right, say an x value of 3, where we had a y value we just determined of 2, and as we continue moving to the left, making our x values smaller, at 2.5 we said we still have a y value of 2. At 2.0001 we still have a y value of 2. And then this third piece is not defined for x equals 2, so I've put a little open circle there. That open circle gets sort of covered by this closed circle down here, and what we're seeing, if we come back onto the graph, the third piece of our piecewise function is a horizontal line or directed line segment that moves off to the right. Every point on there has a y value of 2, and what we have just discovered is, that was terrible, that's better. What we've discovered here is that we do have a discontinuity. So the answer to the question, let's read the question one more time. Find all values of x equals a where the function is discontinuous. The answer is where or when x equals 2, we have a discontinuity. So that's a little bit of a labor-intensive process, but it is a good thing that we went through the motions because we found ourselves a discontinuity. This is another style of question that pops up pretty frequently. And here we want to find a k value that makes this function continuous. So let's look at the piecewise function. the first piece is defined for all the x values less than or equal to 3, and the function associated with those x values is x squared, which is a polynomial, which is continuous everywhere that it's defined, all the way up to the point where x equals 3. And this graph we know pretty well. My parabola that I would normally draw would pass right through the origin for x squared, except we're not looking at this entire parabola. We only are concerned or want to use the part where x is less than or equal to 3. So let me come up here to this point, and I've put a closed circle right there because we are including the x values of 3, so that first piece is defined where x equals 3, and then I'm going to erase everything, I'm going to erase everything that's to the right of it, because that part gets defined by the second piece in our function. And what we want, so let's look at the second piece of our function. It says x plus k. So this is going to look like a line. It's going to have a slope of 1 because y equals mx plus b. There's a 1 in front of that x. And it's a question of adjusting the y-intercept, sliding that diagonal line, right? Like y equals x looks like this. That happened to pass right through that point. I don't think that's going to be the case. But we need to take this line and adjust it vertically, up or down, to make sure that it passes through the right-hand endpoint of our partial parabola. And what would be helpful is if we knew the y-coordinate of that point right there. So let's figure that out. Let's figure out h of 3. So we take the 3, we plug it into the first piece of our piecewise function, we take the 3, we square it, we get, that was a cube, there's a square, there we go. It's equal to 9, so this point right here has coordinates 3, 9. So we need to make sure that the second piece of our piecewise function passes through the point 3, 9. So let's write that second piece as y equals x plus k, and then we know that the point needs to, or that the point 39 needs to satisfy this equation. So I'm going to plug the 9 in as my y value and the 3 in as my x value, and we don't know what k is, but now very easily we can subtract 3 from both sides and get our k value. Subtracted 3 from both sides. There we go. So we've got our k value. And in fact, that's the answer to our question. I glanced up and read the question again, find the value of the constant k. That's it. So y equals x plus 6. 1, 2, 3, 4, 5, 6. The original line would actually pass through that point. And then if we go over 1, up 1, over 1, up 1, over 1, up 1, I did that 3 times, that would land us at the point 3, 9, because we started at 6 and went up 3 to 9. We went over 3 to get to an x value of 3. The actual line would be drawn out of here with an open circle right on top of that closed circle, and then carrying off to the right. If you saw this in a textbook or a more formal illustration, you wouldn't see the closed circle and the open circle right on top of each other, but because I'm writing in 2 different colored pens, it's nice that you can see that the open end of my red line is literally filled in by the closed end of our purple curve. And because the one fills in the other, we have continuity. And here's our last problem for the section, which is our application problem. Suppose that the cost C of producing X units of a product can be illustrated by the given graph. Is C of X continuous at X equals 50, 100, and 150? This is a nice closing problem. Check out your x-axis here. That's an x value of 50. It's looking continuous to me. We don't have to have an elaborate discussion about it because when we run into these graphical situations where we're asked about continuity, we have this nice opportunity to just visually evaluate what's going on. At x equals 100, however, we have a jump discontinuity, and at 150, looks like the function is continuous. So the answers would be yes, no, and yes. Hopefully that gives you a good understanding of continuity, and make sure, the second half of this conversation was pretty straightforward, but the more detailed explanations about using limits in order to test for or determine or demonstrate continuity, that's something that you may very well need to be taking into if you're going from Calc 1 into Calc 2 and you have a different professor than me. You might need to be able to demonstrate those things extremely well. So get those stuck in here so that you can take them with you, and take them with you to the next section. I'll see you in 3.3. Thanks so much.